Phase of the Rube-Goldberg selfie machine. Here we have a marble that's on an incline. It rolls down the incline, it goes to a horizontal section, it travels horizontally, then rolls back up this incline where it strikes these two marbles, transferring its momentum, and then the marble rolls horizontally and triggers the next phase. So let's look at this closer. We have a marble at the top of this incline. Sit on a pool table, and really what we need to look at is the difference in height between here. But before that, let's look at the forces that are on this marble. First we're going to set our coordinate system, be x is pointing down the incline, y is going to be perpendicular to that. So if we look at the forces, we have the force due to gravity, which is going to be pointing straight down. Then we have the normal force, which is going to be pointing perpendicular to the surface. When the marble is moving, you're also going to have the force of friction, and that's going to be kinetic friction, which is opposite its direction. And we could look at all those forces. There's the force of friction is equal to the coefficient of kinetic friction times the normal force. But we could calculate that. We can calculate that the force due to gravity in this component, the x component, is equal to g times the sine of theta, is equal to 5.5 meters per second squared in this case. But I'm going to look at it through kinetic energy, potential energy. So here we see that the height difference, 0.51 meters, is going to result in a difference of potential energy between here and here, according to the equation mgh, or the mass of the marble times the gravitational acceleration times height. And so we have 0.51 meters, we have a mass of 20 grams, so our potential energy difference is 0.10 joules. So 0.10 joules here. As the ball travels down, its potential energy here difference is going to be 0, and that's going to be converted to, if it was frictionless, kinetic energy, which would result in a velocity in this direction of 3.2 meters per second. However, that didn't happen, so because we're not living in a frictionless world. So then the marble would move back up here, and then it would the kinetic energy from here would be converted to potential energy here, and the marble would then be transferring momentum here. So if we looked at the kinetic energy here, okay, so if we look at what the velocity would be here, well, this is 0.325 meters from the top of the pool table here. So the difference in height between here and here would result in a velocity, or the difference in potential energy, and assuming that's converted to kinetic energy, then your velocity here would be 1.9 meters per second. Pretty fast. However, what we saw in actuality was it was barely able to make it this high, even though it started out much higher. So if we looked at what happened, again, we have the force due to friction and the work that from friction as it travels this distance here, which would then our kinetic energy is going to equal to our potential energy minus the work due to friction. But also we have to look at the ball, or the marble was rotating. So then some energy was put into changing the angular momentum of that marble. And so down here, our velocity was much lower than predicted due to those effects if it had been a frictionless surface. So then when it came up here, it was very much slower. That's why this distance, we actually experimentally determined this distance. We initially had a much taller incline, and through several iterations, I figured out how high that the ball traveled, or the marble traveled. I cut a little bit lower than that, so we would have enough velocity to demonstrate the momentum change here.